Like it's about 3:30. We're going to go ahead and get started with our next session. I know we haven't started yet, but I've already been told that this is the best panel of the day. So I'm super excited, super excited. All right, some more folks will probably trickle in on the way here. I passed through the bar and I figured out where everybody's hanging out. So they'll probably join us here momentarily. So I'm Dave Robau. I am the CEO and Chief Garbologist at National Energy. I'll talk a little bit about myself in just a minute. I really want to focus on this amazing panel that Gene has put together for us. But first I want to say what an incredible day we've had so far. How about a round of applause for Gene Jones and his staff and all the amazing work that they do. And yes, I'm trying to earn some more free drink tickets. So, a couple of quick things. You'll notice a QR code here. I won't read the full bios for our panelists because it is extensive. So if you want to scan that QR code, you'll be directed to the compendium for the conference and you'll be able to see all of the bios that are listed in the program guide. So, rules of engagement. Each of our presenters will come up in the same order that we have listed on the agenda, so this order here. They'll make their remarks either here or down at the floor, and then we're going to come back as a panel and I'll moderate a Q&A. But if you have questions during their presentations, I'm sure it'll be fine. Just know that that's kind of the flow and kind of what we hope. Now, the other thing I want to mention is the setup for this room is very deliberate. So this is a classroom setting because the idea here is for you to engage with this panel. It's not us just talking to you. Our goal is we create a little bit of a back and forth and some dialogue. So as you're going through the presentations and you're listening to the information and you want to jot down questions, the very back of your program has a section that you can use to jot down some notes. It might be helpful just to kind of do that. So I'll introduce my panelists and then I'll give you a little bit of bio on myself and then we'll get started with the first presentation. So on the far end is Dr. Steve Wong. He's the CEO of Fukutomi Recycling. Next to him is Ms. Lisa Puckett. She's the Chief Compliance Officer, BayArea Compliance. And in the middle here is Steve Napolitan, CEO for WastAway. Mr. Jordan Klinger, with the Department of Energy's Idaho National Labs. And then finally, Ms. Varsha Walsh, CEO of Offstream. So this is our panel. How about a round of applause for our panel? Great. So this will be the order that we kind of go in. I'll go first. Since I'm already talking, I'll give you a little bit of background on myself. I have been in this industry for about 25 years, plus or minus. I'm an environmental scientist is my background, and I'm focused on putting an end to landfills as we know them. This panel will be focused on innovation in waste conversion, so it's a very timely conversation. So I think what you'll find over the next 2 hours of conversation is some really in-depth information on kind of the state of the market. And then at 5:30, because I'll be doing my job, so at 5:30 or a little bit sooner, we'll wrap this up and then we can take the conversation out into the exhibit hall. Does that sound good? Okay, so let's go ahead and let's get started. So like most of you, I was minding my own business as an environmental scientist working for the Air Force, and I got thrusted into the world of garbage, and I've never looked back. My career started halfway around the world working on this issue. Who knows what this might be? I know you know. Anybody know what this is? This is what's called a burn pit. So I was at Air Force Special Operations Command, not too far from here at Hurlburt Field. Any Air Force people in the room? A couple? Okay. So I was up at AFSOC working on some pretty cool energy projects. And burn pits came into my vernacular. And what we found is that this is how the military was managing waste in what we call the AOR, the Area of Responsibility. So in combat zones, as you can imagine, not a lot of recycling. Most of what comes in to a forward operating base is designed as single use. And as you can probably imagine, this material starts to pile up. So somebody in the Department of Defense decided, I have an idea. We're going to dig a hole in the ground, and we're going to put all this stuff in it, and we're going to pour jet fuel over it, and we'll just light it on fire, right? What could possibly go wrong? So it turns out quite a bit. The Department of Defense estimates that about 3.5 million veterans have been impacted from burn pits, from the toxic emissions and the exposure to these materials, because as you can imagine, this was the primary form of waste management in combat zones. And burn pits, unfortunately, were everywhere. And anything and everything that you can think of went into a burn pit. So this is an example of what it looks like when the material gets deposited into these holes, and it's anything and everything that you can think of. So batteries, plastics, all kinds of metals that are all causing all kinds of issues. So my job was to develop first of its kind technology to be able to end the practice of burn pits. So thankfully, technology today has evolved to the point that now this is not a practice that's used any longer. I will tell you the journey that I've been on for the last 15 years has really allowed me to leverage technology to solve environmental challenges. So this is no different. We built first-of-a-kind technology using taxpayer-funded dollars, so thank you. I appreciate all of you for paying your taxes. And as a side note, if you're interested in putting your marketing dollars someplace, I highly recommend the New York Times. When this story ran, for the next 3 months, we had inbound calls on communities all the way around the world, places that I had never heard of. Does anybody know where Benin is located? In West Africa? Well, I found out it's in West Africa. So what was interesting about the project is it was like I mentioned, it was a one-off, so it was a bit of a science project. But for me, what it did is it reaffirmed the fact that waste, if treated properly, could help solve other issues. So in this case, we were able to produce power in forward operating bases where getting fuel and the logistics associated with that was very, very difficult. But for me, it put me on a journey to say, hey, what else can we do with this material if we're able to pull out the inorganics out of the waste stream? So I'll spend a couple minutes talking about that. So what I realized is these landfills are really bad for the environment. They pollute the air, land, and water resources. I always say there's two kinds of landfills. There's ones that pollute the environment, and then there's brand new landfills. So landfills are the third largest source of greenhouse gas emissions. But what if I told you that that organic fraction that's causing all of these issues and climate instability could actually be used to solve the issue around climate? So that's what I'll spend a couple minutes talking about. So the reason we get so excited about biomass because it is everywhere. It is abundant. And what we've learned on our journey is it's not just the organic fraction that's in the municipal solid waste stream, but there are other materials such as vegetative debris after a storm, the solids that come off of a wastewater treatment plant, even the organic fraction of the construction and demolition debris, which dwarfs the MSW sector, could all be used as a potential fuel. So here's what I'll kind of walk you through. So I'm a bit of an energy nerd, so we look at about 5 different technologies that are considered renewable, and of those 5, there's really a subset of those that are able to meet what we call baseload power demand. In other words, you flip the switch and power comes on. So wind and solar are what we refer to as intermittent technologies. So basically what that means is it's weather dependent, right? So the resource is not available 24 hours a day, 7 days a week. So those are intermittent forms of energy. But now if you take a closer look at the versatility of this material, that's where biomass really stands out. Because if you had a thermal load for, let's say, a wastewater treatment plant, or if you were interested in producing a renewable natural gas, or perhaps you wanted to create a liquid fuel or electricity or hydrogen or sustainable aviation fuel, you can do all of those things with biomass. So the challenge is finding the right technology to be able to extract the materials that don't convert into fuel or have a higher value in the circular economy. So I'll spend just a minute talking about that. So what we've done here recently is we've introduced a little bit of a new, or I should say novel, business model, and that's called recycling as a service. So just with a quick show of hands, how many people in the audience are representing either a municipality or a county, whether it's a city government, town? Okay, so the challenge that these customers have is they want to implement recycling infrastructure, but they just don't know how to pay for it. Because sometimes we're talking about a $15, $25 million solution, and it's difficult to program for that in your budget, right? So these solutions are cost neutral to the customer. So recycling as a service basically means the customer is not making a procurement. They're contracting a service. So there could be a 15-year service agreement with this recycling as a service business model so that there's no capital expenditure on the part of the customer. The other thing that's interesting is customers are really just interested in the service. They don't really care how they get there exactly. They're interested in landfill diversion. They're interested in increasing recycling. And these technologies allow you to do that. The other part that's interesting, I don't know what happened to my graphic there. I created this with ChatGPT, and apparently there's only 7 states left, so I'm not sure what happened there. I'll have to converse with Grok and see which states are remaining. Let's just assume Florida is one of the 7 states left. This is an issue that gets overlooked, and that's the returning these critical materials back into the domestic supply chain. So things like copper and steel and aluminum, these are all important components that need to go back into the industrial base. What we've learned through COVID is we became incredibly reliant on other countries for these raw materials, and disruptions in supply chains have really impacted the way we live and the way we manufacture things in this country. So for me, I am a certified tree hugger, unapologetic, card carrying, the whole 9 yards, and that's really why I got into this business, was to be able to make an impact and create a better environment for my children and your children and their children. So these are all components that are important, and then what I call the Jedi effect, oh, no, sorry, not that Jedi, this Jedi, jobs and economic development impact. This is where companies like National Energy come in and make an investment into the community and build out all the infrastructure and hire the jobs, or rather hire the local employees and create economic opportunities. And the reason that this panel is here, or I think part of it, is the growing demand for energy is getting ready to increase exponentially. Does anybody have any guesses as to why that might be? How many people have used artificial intelligence to do an inquiry? Anybody use ChatGPT or Grok or some of the other ones that are out there? I ask this question a lot, and every year more and more hands go up. The impact of data centers is just getting started. Data centers draw approximately 4% of the total energy load in America, and that's getting ready to increase exponentially. So by 2035, 10 years from now, data centers are expected to make up about 12 to 15% of all energy use globally. So if you're bad at math, that's a 183% increase in the amount of energy that's needed. So our panel is here to focus on conversion technologies that will allow us to be able to meet the growing demand for energy. Oh, and we only have 2 hours, so no pressure. So our job is to come up with the solutions to be able to leverage some of these technologies. So with that, I'm going to be done talking for a minute. Please reach out to me on LinkedIn. I love connecting with people. We have a community of about 21,000 people, and we talk trash and just all kinds of fun stuff. So we're also exhibiting here. If you want to stop by booth 13, all of my contact information is here. And as we say in the garbage business, I'm at your disposal. And I'm going to turn it over to Steve. You are up, sir.
Yes, good afternoon. Thank you for the very interesting introduction and also your presentation as well. It's a lot that I just learned just now. Thank you. Okay, today my topic is about chemical recycling and plastic circularity. And when we are here with Gene Jones, or Mr. Gene Jones, we cannot afford not to talk about agricultural plastic waste management. So that's why this is also a topic that I will include it. I start with a number of 9%. I don't know how many of you understand this 9% and then where this come from. First of all, this is the number that I obtained from the UN Environmental Program. And although I argue with them that might be today we have more than 9%, nevertheless, they said this is the number that they have from the literature. So I will use this number. And then from this number, we will see, especially in this country, we actually recycle only 9% of the plastic waste. Before I move on, I will distinguish between plastic waste and plastic scrap. It's very important that for people that in our industry, we always call it scrap or material. For people that they don't understand, they call it waste. So I will actually distinguish between waste, which is coming from municipality, and also material that will never really get sorted. So the recycle of this 9%, right, because these are the sorted material, and the rest, right, there will be 12% for incineration, and the rest will go to landfill. And I believe some of them actually end up in open environment. So what happened is, right, the reason why there's more going to landfill or incineration, because mechanical recycling is very complicated. And also plastic is really, really different than any other of the resources. I don't know whether any one of us here that realize there are more than 100,000 different types of plastics. Because when you mix two plastics together, there's one polymer. And then when you put additive in it, it's another one. I think normally most of the people are familiar with 1 to 7. With 7 is any other plastic. But this okay, will make these things complicated. And before I move on, I also want to share with everybody that, in fact, I'm in this recycling business for 41 years. And we have come across with different type of material. One of the things that might not be familiar with most of the people also because each material carries different mechanical and chemical property. With these differences, right, you need to have the machine, you need to have the skill and technique plus the correct temperatures. So that's why it makes things complicated. And the 9% because also you can only recycle material which is already sorted and also single material. Why we end up only 9% also because of mechanical recycling can only do so much without talking about the economics of it, especially nowadays. Prime material is so cheap that you probably would not choose to buy recycled material. And this overcapacity and also low prices are impacting not only US but also Asian countries, including countries that produce plastic material with also low labor cost. This is one of the main or one of the reasons that we don't really see when the price will go up for prime material with all the overcapacity situation in different parts of the world, including the US. And the drawback about mechanical recycling, because later on I'm going to talk about chemical recycling, so I have to talk about the drawback of it. As we just noticed that you can only recycle material which has been sorted with like almost 100% purity. And even you have all these things, right? One had to understand that. So each thermal cycle shorten polymer chains. That means whenever you recycle material, it will degrade mechanical and chemical property. And at the same time, there is also situation Where later we also will look at it. Okay, brand owners, they always say we're going to use 30% recycled content, 50% or 100%. Actually, this is not possible. As I just mentioned, every processing reduce the polymer chain. And then, so we look at, the last bit, the downcycling problem, right? So from prime virgin material to cycle 2, the quality, we also downgraded, and then ultimately there's not much application that we can use for the recycled material. Yeah, I also like to give example of agricultural plastic waste. Most of the agricultural plastic waste, they are contaminated. I think the best recovering rate I see so far is a greenhouse film, which might recover 70–80%, the best scenario. Then the rest, we have a drip hose, drip tape, we have a silage film. The worst one will be the mulch film. With the mulch film, we only recycle, or we can recover only 25%. The problem is challenges of recycling, at the same time, the cost of doing it. Give example of like prime or off-grade polyethylene, nowadays about 700 or maybe maximum 800 for off-grade. And the cost of doing this one, in Europe, we talk about 1,000 euro at least. In the US, I think we also have to talk about at least probably a few good hundred or up to 1,000. So we're going to move to waste localization. But before I talk about this, I also talk about Basel Convention impact. I think recyclers or exporters in this country, this is a luxury for them that they don't have to deal with the Basel Convention because U.S. is not a party to the Basel Convention. And as also U.S. policy tend to be free movement of free exports. Whenever the country can do better than recycle domestically, they will tend to export to all these countries. So U.S. is the only developed country not the member of the Basel Convention. But at the same time, there are more than 190 countries that are members. And so nearly all the developing countries, they are members. So when I say they are members, right, so it means if U.S. don't care, but then all these important countries, they have to care. And the latest situation is like Southeast Asian country, they really don't like to import plastic waste at this moment. After 2018, China put an import ban. Southeast Asian countries also experienced the problem that China used to experience. And then they also found out that to import plastic waste or plastic material, they don't really make a lot of money from like recycling, especially lots of lots of residents complain, and lawmakers they have to listen to what the people say. So Malaysia is the most recycled country. As we are talking nowadays, they also putting a stop, for importing of not only from the U.S. but from the rest of the country as well, or from the rest of the world as well. So this is the situation, and because of this, we have a transboundary movement of waste from one country to other country, and also the whole situation is right. No country like to recycle other countries' waste, and especially this is polluted. When you turn on CNN or BBC, there's always a turtle, like in the ocean, being choked by film or by garbage from the plastic. So all these negative news about our recycling industry, and what I see, and I think most people agree, this is becoming a really localized business, especially when we talk about greenhouse emission. You have to ship something from here to the port to the importing country, and all the costs involved is also the economics doesn't work. Then the problem is we actually have a situation where mismatch of industry or mismatch of material or mismatch of material that generated in developed countries, and we also have a mismatch of infrastructure located in a country or in places that they can recycle economically a lot cheaper. And so this mismatch, right, I think one had to deal with. And then with the Basel Convention, we also have a different regulation from the EU. We have a European Union. They also have different set of regulations restricting transboundary movement of waste, and also OECD. What we do, right, maybe we had to look at domestically, if we can do it, and if we do it, what kind of technology or what way, we can do it. So now I come to chemical recycling. So chemical recycling, I think later on we might have two expert panelists. They are also sharing gasification is also one of them. And the most familiar one I know and I've seen, will be the pyrolysis. And I think pyrolysis is also one of the solutions. Nevertheless, we talk about economics. In principle, it is not easy to do chemical recycling or pyrolysis without support of different kind of regulations or mandate. My colleague Lisa is going to share what's ESG and also compliance. This is what we need. To give an example, with pyrolysis, we still have to, I don't know whether we had to pay for the feedstock, but we have to pay for the transport. I don't know whether there's any tipping fees. And then the processing, right, we still have to sort, but we allow, or the process allow to have certain percentage of contamination. And afterward, this is the most interesting part. We know that the fuel derived from, when I say fuel means oil, derived from the pyrolysis. Commercial value of this, right? I have example of this in Malaysia. They probably can only sell $300 to $400 per ton. But this few to $400 per ton, right, with the investment of machinery, all these things together, it's not going to work, So what we need to do, right, is we still need support of like system mandate. And yesterday we talked about EPR. And we don't know how this works, Yeah, and then I was trying to find out, the economics of this, and then also to have an example. But one thing I know, from my experience talking to people that they are doing this pyrolysis, there's a company in Mexico, Mexico City, and they have machine, invested, and English design and made in Eastern Europe. So what they have, right, is they get support from brand owner like Nestle. So they pay them certain amount per ton. And then their output, they sell to petrochemical company for 1,000 something, which is about 3-4 times more than the commercial value. I think that would be the way, that would be the incentive, or that would be the thing that to make economically viable. So because I don't go through all this detail, and I don't know how much time I got left. Yeah. So then the next thing is about pyrolysis. We have like different kind of pyrolysis, as I just mentioned. We have gasification. I'm not going to go too detailed about this, as we have two experts over here. And then pyrolysis is the one that I've seen the most. They are the one to process PEPP, polyolefin. And what we do, right? I know that there was somehow there's a lot about energy consumption. But what I experienced or what I have seen with PEPP polyolefin, for example, from packaging material, probably they can recover as much as like 70-80%, of the oil, and they also have some gas. But then this gas, if you can use back, to heat up the chamber, this could be or the system, So this, could be a feedstock, for energy to process. So I don't really see, some of the things that I found. They always commented, this is like intensive energy consumption. I think maybe my other two panelists should be able to share, where, they use the energy. And then the other thing I like to mention about this, right, is the pyrolysis, right, and also chemical recycling. We don't really see many success cases, partly because of regulations and also because of the economics. I don't know how many of success case we have seen or we have come across in the US, but I know for sure in Europe we don't really see many. Partly because of the regulations and also because of the economics. And for regulation, in this country, we know there's more than 25, 26 states classify pyrolysis or chemical recycling as advanced recycling. Because of this advanced recycling, the operators or the factory is able to claim some kind of subsidies from brand owners. And then for Europe, I know there's a lot of big company, they put a pause to do pyrolysis because the EU have not approved this pyrolysis or chemical recycling as advanced recycling. Because of this, so they also don't get subsidies or they don't get like so much money per ton, from brand owner. So let me move to the next one, and then we have the advantages. I already come across with some of the advantages when we compare with chemical recycling. Especially for packaging, although we see nowadays the most recycled PET and also HTV bottles because these are easily sorted and also easily identified. But for other packaging or soft packaging, because of the lamination, additive, all these things, we probably have to do this one or we have to collect them. One might not be aware that, for example, our chocolate bar, this packaging, I don't think this never get recycled because of the collection. Yeah. But on the other hand, if there's a deposit, for a small chocolate bar, yeah, I'm sure that a lot of consumer will return it. So system is also another thing. But when we talk about system, it's very, very complicated because we talk a lot for the last probably 2 decades. So far, we only see collection of PET bottle, collection of HDPE bottles. And these two material, they're now selling above or they're selling more than prime material. So now the problem is about traceability. Who can trust or there should be a system. And I see nowadays there's some organization or certified body, they use blockchain to make sure that from the very beginning, from how the material or the waste collected and going through a different process. And they have also video and also they post or they share this one or they digitalize this, okay? So I think that will be the future technology to have the chain of custody. Again, okay, this system, Lisa will be able to share a bit more. I also mentioned about current challenges, and some of them, like the first one is about 50 million to 200 million capital expenditure. This is also something I like to address because I don't know, some of us might be aware that in China or in Southeast Asian country, you have to pay, for the used tire to do recycling, to do pyrolysis. But in this country, you actually get paid to take the tire, used tire, because there's overcapacity over there, and also because they don't really have to invest so much money. I always share with people in the business that I have this number, 50 to 200 million from also ChatGPT, okay? So most of the people, they invest this kind of money, but then if you invest a machine from Asia or from China, you probably pay, a fraction of a fraction. Yeah, but of course, okay, you have to comply with all the regulation, health and safety. Yeah, this is the most complicated part, but it's not impossible, I would say. So with all this situation, the cost being so cheap for processing and also the capital investment is a lot less than what we have to invest over here. So there's a lot of manufacturer for pyrolysis machine. They're exporting to other developing countries, including African countries, South Asian, South American countries, as well as Middle East. So that's why pyrolysis is something that for the future, but at the moment it's already started in Asia, in Asian countries. But I just gone through the energy intensity, the technical capacity. This is the thing that we also have to look at, especially when we are in the U.S. If you want to invest something in pyrolysis or chemical recycling, the equipment, same as like you build an aircraft, you cannot afford to have any mistake. So once you have mistake, maybe you are finished. Okay, you have to close down your factory. And also see the emission. Okay, yeah, I think what we find, from the OpenAI or from ChatGPT, we always find information about emission management, all these things, and we also find residue. I think depending on what, like you recycle polyolefin or recycle used tire, there's not really a problem with the residue. Yeah, unless, this is something hazardous, then you might have to use different system or different technique. And then talking about emission management, of course, this is something that we have to care of, and there's a way to do it. Yeah. So now I still talk about ESG as I just mentioned. I also mentioned about chain of custody, traceability, and also profitable carbon reductions and premium pricing models. So when we come to a regulatory landscape, EU have a different situation, and we had to bring in EPR, we had to bring in recycled content as a mandate, especially by 2030, there's a lot of mandate or regulations that we have to use so many percent of recycled content. And next thing is mechanical and chemical recycling, or this is a complete circularity. I think a lot of industries really worry about chemical recycling will replace mechanical recycling. Actually, these are two different things. They have to work together. When they say they have to work together, so this is a complementary relationship. Mechanical recycling, you have to sort material very, very clean, almost free from contamination. And for chemical recycling, the threshold is a little bit more flexible depending on what, and also the machine, what material, and also how the machine can take, and what material the machine can take. So then we have a complete circularity. And then now, so they are not really competition, they are complementary. And the next thing, going forward, we have a future outlook, 2030, as I just mentioned. And also, this is a big business that we will have lots of money involved in terms of billion, but I think it's more than billion. When you look at so much, in the around us for the waste to be recycled. Again, these are the last couple of pages that I share, and we can also share, our presentation. Yeah. So essential complement. So this is the thing that we need to have technology, we need a regulation, and also collaboration. Yeah, this is what I had, to share, and thank you.
Release the slides for the conference, as far as I know. So you should have those as a compendium. So Lisa, I'm going to bring you up, and the floor is yours.
So now I'm not nervous. Hi, my name is Lisa Puckett, and I am the Chief Compliance Officer and CEO for BayArea Compliance. Today I'm going to be hyper-focused. Am I supposed to do the flicky flock thing? Okay. Okay. No worries. I'll go ahead and continue with my introduction. My name is Lisa Puckett, and I am the Chief Compliance Officer for BayArea Compliance. And today I'm going to be mainly focusing on our Net Zero 360 Sustainable Waste Division. And we're going to be really diving into how compliance and net zero work hand in hand. Oh, the wait time? The breathe.
Yeah, he's working on it.
It's okay.
You want to expand on your bio?
No. La, la, la.
Since we're waiting, can we ask or just add a little bit to what Dr. Wong was talking about earlier? So, I'm John Potty, something that we see in the U.S. is, the struggle between, I'll cut it off as soon as it gets ready here. The struggle between, the feedstock for the feedstock process material, and then transporting that feedstock. So,
Yeah, that's fine. Okay. I have
Transporting that material costs a lot because it has to go to areas where we have refineries for to make this chemical process work. You're either transporting it in a raw form or film bales, or you're transporting it as a liquid, and both of those get very expensive. How do they mitigate that in the Asian regions that you can.
We're over time? Okay. Well, I'm only 5 minutes. All right, let me reintroduce myself. Thank you guys for patiently waiting. So as I mentioned, my name is Lisa Puckett, and I'm really going to be hyper-focused today on our Net Zero 360 program. We are going to really be diving in to the gap between technology and execution and why Net Zero 360 exists to close that gap. Okay. Our industry has invested heavily in innovation. Mechanical recycling, advanced material recovery, pyrolysis, chemical recycling technologies, but technology alone does not bridge the gap, right? Infrastructure does, system design does, and when infrastructure doesn't exist, here at BayArea Compliance and Net Zero, we build it, okay? There we go. Every single day across our transfer stations, we hand sort over 10,000 pounds of plastic. Plastic that previously had not been, it had been designated for landfill or just strictly and directly waste to energy. Ultimately, we bring that into our facility, solve complex problems every single day. Whether it's medical waste plastics, hazardous lab debris, contaminated streams, or even vape device recycling, we identify that gap, we engineer the workflow, and then we operationalize the solution. Our systems work across all industries. We work with municipalities, educational systems, veterinarian offices, healthcare, whoever has the issue, we come with a solid solution. Because mechanical recycling fails without clean streams, and ultimately pyrolysis would also fail without consistent material inputs, as we just talked about. Circular systems will fail without disciplined separation at the front end, and so that's why we work on the generator side. And we think of us as the in-between between the generator and the actual manufacturers and processors. We work with janitorial networks. We work with MRFs, okay? And I mentioned school districts and education systems. We have internship programs to involve local communities and increase the economics behind the education piece of that. Okay. I know Dr. Wong also had mentioned, we partner very well. Dr. Wong was really talking about policy versus goals versus operational reality whenever it comes to feedstocks on these products. And we know that there's a lot of different complex regulations that we deal with. Every single day, as a compliance officer, I'm dealing with ESG, project management, sustainability goals from the corporate side, whether it's healthcare, biotechnology, device, for example, very complicated requirements. Now, what we've achieved is the ability to create a full circular economy. We certainly want to expand on how many times any item could be recycled. That's our first path. Our first path is to reuse, and then we're going to recycle, right, mechanically. And ultimately, we want to avoid landfill. Okay. A little bit off. See what slide I'm on. Sorry. Now, because we know that you cannot manage something that you're not monitoring, right? And you really need to know what the problem is before you can address that problem, and you can figure out the correct way or the path for that product. Some things do need to be in landfill. I mean, that's just the reality. Landfills are super important. Some things need to go to waste to energy. They need to be recycled. They need to go through pyrolysis. We monitor each item from the procurement level, teach generators how to segregate that material so that we can reclaim the value that it's intended for. Now, as you can see here, this is our Net Zero 360 dashboard. This is actually just a quick demo of it, but this helps our clients create an ESG story, not as a punchline, right, but an actual process. And ultimately, our Net Zero 360 measures input from the materials that are hand sorted at the site or the generator site. Additionally, again, once it comes into our facility, we hand sort, we measure contamination, and then we measure the output, depending on what type of plastic it is or what type of material. It could be vape recycling, it could be metals, it could be cardboard, right? So we look at the entire picture, and that way our clients can come up with the best approach for what their issue is. Some are really geared towards sustainability, some more so, they want to save money. They want to cut transportation costs. They want to cut medical waste costs. And so we have created this infrastructure in order to tap into local partners and to the people who are best suited for that waste stream. In a circular economy, we're not the processor, so to speak. We're actually the orchestrator, right? And we connect generators to the appropriate recovery pathways, and we ensure the feedstock quality consistently. Circularity is not a promise, it's a system, okay? And systems require operators. And Net Zero 360 converts complex waste streams into measurable ESG value. We track landfill diversion, Scope 3 impact, and we track material circularity. We track avoided virgin excellence within it. All right. And that brings me to my closing thought. As I close today, I want to leave you with one thought. Net Zero 360 is not a program. It's a shift. It's a mind shift. It's a process shift. And for too long, compliance and sustainability have been operated in two separate lanes. Environmental risk is compliance risk, and operational risk is environmental risk, right? So the future will demand that we treat them both as one. The organizations that lead next will not separate responsibility from the strategy. They will integrate it. They will operationalize it, and they will prove it. The Net Zero 360 program exists for that moment. This is being led by a woman-owned, execution-focused organization that understands both compliance and circularity. We are not observers in this transition. We are builders in it. We are operators within it, and we are proof that leadership and infrastructure go hand in hand. That moment is now. My question to you, are you ready?
Steve, I'm going to turn it over to you. I got your clicker here, and you are armed with a microphone.
Okay, I got
The
this
floor
one
is
too,
yours.
yeah. Thank you, Dave. I can't stand behind a podium, sorry, so I'm going to make it more lively here. So I'm Steve Napolitan here with WastAway, and I just want to first, thank Dave and all the other fellow panelists and Gene putting all this together, and Tim and his team with the AV. Thank you. The conversion is the conversation. That's what this panel's about, and that's why we're here. So, I just by a show of hands, how many of you see that the waste, the trash, is going to just keep on coming, right? Okay, you knew that the answer was there. I just want to see if all your arms work. Okay, good. So we're still alive, and here you are. Okay, well, this is a gigantic issue, right? It's not a solution, it is a long-term liability. And, Dave and all of us will talk about this. There's so many toxins and things, and this is not the way. And so I'm here to say this is what we need to change. This is going to keep happening, right? Our population, and what is waste by definition? That which is no longer useful, right? That's what we thought, right? But what if we can make use of that, right? How many would want that? Right? Okay, so we're in this room for that. You came here for that conversion, and then let's talk even further. So look at this. From my team, from multiple sources, we're about 8% in the United States of our energy demand is from renewable. 8%. So there's a huge room for growth, right? Who's with me? There's a lot of room, right? Here and okay, now you're sick of me asking questions, right? I could already see you falling off there. We got to make this interactive, like Dave said a second ago. So this is where WastAway comes in, because I'm looking at what no longer is wanted, our municipal solid waste, and then what we all need and what has been brought up, the demand for energy is only going to go up exponentially, right? So this is gigantic. Not only is it something that's needed right now on our planet, but it's also a huge opportunity. So this is what I'm here to do. And so for me, I've been an entrepreneur my whole life. And I've now, for the last almost 20 years, have been coaching, consulting CEOs all around the world. And one of the investors and board members of WastAway was a client of mine and said, hey, I need you to come help. So a little over a year ago, I started helping. And then you could say I got bit by the bug. And I'm like, well, this is something I can get behind and help with all of my experiences to make this scale, because we already have operational. And I'm going to explain that in a second. We're already operational. This next phase is about scaling. And you can see the huge gap that we're about to fill. And so my mission right now, and to speak to you as WastAway, is that we're going to make the greatest use of waste. And I don't have all the answers. I don't know if any of us do, but we're working towards continually learning and finding the best way that we can take this thing, waste, that keeps coming, and make the best use of it. Everyone with me? Yeah? So here's the deal. One of our plants, if we're going on an average of 400 tons a day, and we can scale through some of our partners, 10 tons an hour to like 50 tons an hour, depending on the application, depending on the output. And I'll get more detailed into what we do in a second. But just one plant, if we base on 400 tons of municipal solid waste processed daily, can remove the equivalent of 96,000 automobiles from the road, if we talk about the equivalent of the carbon reduction. Another example, over 500,000 trees a year in one plant, equivalent in carbon change. And then over $800 billion of carbon in just one plant. And that's 400 tons a day. So you can do the math on like other, different municipalities around in big cities. This is still scratching the surface. So just as this scales, look at how much change we can make. Now, the next thing to say is that so much of us, when we're talking about recyclables and we're all talking about that, we have to divide these things up. We have to have, separation. When you have source separation, there's a lot of cost. And, we all know there's certain states and municipalities that are requiring this. And so now in some places you have 3 trucks going around. So now we talk about the carbon impact. We have, 3 different trucks coming around, 3 different bins, and then we have massive amount of contamination because it's not even source separated by the consumer in a proper way. So we're not really doing the job, and it's costing more money. So a lot of all this is cost centers, right? And especially for those of you that are in a municipality, these are all costs. And so this is a problem. So when we work with this, we'll take 100% of the feed. And if you already have MRF, or you're already source separating, then we can work with that too. But we can take all of this, and then and I'll go over the process in a second. Obviously, we have our own sorting. We will use a MRF. We will do all those things, but then we're going to be able to convert that into different energy sources. So 70, and this depends. The reason it's not an exact number is because depending on the application, the thing about WastAway is we're not contingent on one type of fuel. We can do solid fuels, we can do gas, even liquid. Like, there's many different things that can be output, and so we'll look at the geographic area and what is the application necessary. What best energy is there, even if it goes to electricity. These plants could be put onto a grid. So the conversion will vary, but we can say definitely over 70% of this municipal solid waste will be able to turn into a fuel. Okay, and then this also, with our patent product here, we also can do this at 0 pathogens. This is sterile and stable, and that's one of the unique things about our technology, is that we can do that. So, and we're also continuous feed. And I'm skipping ahead. I have a slide for that, but that allows us to no longer be MSW. From the time waste hits the tipping floor at a facility like this, or our facility that we have already, then in 30 minutes it's no longer MSW. And we've worked with the agencies, including the EPA, so that we actually have that where it's no longer MSW, because it's now sterile. And that's what makes us drastically unique, and that it's continuous. There are other technologies that can make things sterile, but they're not continuous. And this is very, very important, because speed, if you're getting trash all the time, every day, you have to be able to process that continuously as quickly as possible. So you're probably saying, okay, you're saying all this stuff, Steve, how does this work? Well, I'm going to go through each of these, but you have your input. We're going to process. We are going to sort. We're going to grind and shred. We're going to get the recyclables out in that stage. Then it goes through our cellulator. That's most of our patents. We also change some of the process design and systems throughout this, and so we have patents over the whole process. But then we can convert that into a multitude of different energies. I'll talk about that in a second. And that could be, again, a lot of our projects are going to be, right now, RNG is a great thing, but we don't have to do that. And then we can also go to a solid fuel. So let's go over each of these steps. So again, 100% raw unsorted MSW. Now this is significant, because this can be cost savings to whoever is handling that. Because now no longer do you have to worry about that. And even the consumer doesn't want to worry about that. I actually lived in a town in California, and it was like, oh my God, everyone went crazy. And some of you might look it up. It's called Roseville, California. It's outside of Sacramento. But see, I grew up in San Jose, California, and they're my fellow panelists here. But I've, a long time been sorting into 3 bins plus your trash bin, so like 4 different things. And I thought that's a lot, but then I was talking to some of the European counterparts, and in like Germany, they're sorting like 7 bins, and each glass bin is a different color. So we think, holy cow, it's a lot of sorting. And then Roseville got a MRF, right? So now let's let the machines sort this out for us, and it can be done at a better job. So this is how it starts at the front end. And then in this process, we're going to retrieve all the recyclables we can. What the difference is for WastAway than just a standard MRF. And I say standard not in any demeaning way. I mean, but basically, what MRFs are doing, they're sorting for maximum recycle. We are recycling too, but we're maximizing the sorting for the maximum fuel for the maximum energy that we can have on the other side, because that's what we want to maximize the BTU for whoever our energy user is. And so we're retrieving recyclables, we're grinding and shredding, preparing the material for the cellulator, which this is the step that allows continuous feed, that allows it to go to pathogen-free so that it's no longer MSW. So once we get through there, about 30 minutes from the time the waste hits our floor to this point, it's no longer MSW. And this is the crazy part, right? And then also I'm gonna say it adds, so then we've been doing a lot of work with anaerobic digestion. How many of you are familiar with anaerobic digestion? Some of us, a few. So this is a process to pull the gases out, and then with refinement, you can actually create renewable natural gas. You can also refine it into propane, other things, liquid CO2, like there's different things that could come out of anaerobic digestion. But what's significant and why our partners, and these are billion-dollar companies with hundreds of anaerobic digesters around the world, want to partner with us is because they're traditionally having to work with the source-separated organics, or they're working with dairy manure, and that's the main things. There's other things, but that's what they have to work on. We open up the market to all MSW because we can actually bring this as a sterile feedstock into their anaerobic digester, opening up markets that they could not touch. And this is where we're actually scaling right now. We have multiple projects around the United States and the world now because of this opportunity. And so then we can create more renewable natural gas than what they were doing before and open up places where they weren't having dairy waste or just those source separated organics. So we open up their feedstock potential, which is the big differentiator for WastAway. And we're really excited about this because we can start producing a lot more energy and fuel. Well, fuel to make the energy, right? And so this is now also the biggest thing with anaerobic digestion is that a lot of anaerobic digestion, they have to give away their digestate. So after this, it goes through this bacterial process, pulls out the gas, and then they have this remaining. And some make compost. That's really hard because we want organic compost and we don't want to put other plastics or things back into the land. So that's been more difficult if it's not clean. I have been to facilities where they have such clean organics that they are able to make compost, but it's not many. Not many at all. So what happens is, because of our process of sterilization, we actually can sell the digestate. So this brings another revenue, because now we can actually take the digestate from the anaerobic digestion and still have material, because it's only taking the gas out, we still have material that we can actually sell as a solid fuel, and that can be replaced for coal burning, other pelletized burning sites, cement kilns, and we could also make compost as well, and a multitude of other things. We've also we've done some testing on biodiesel as well, coming from this feedstock. So it makes a multitude of things, and ultimately what we're taking is a waste, which is a cost center for most people, and we're turning it into a revenue engine on multiple standpoints. And this is now, I think, hopefully you can see why I'm a little excited to be doing this, because this is the change that we need to see in the world. And I'm not saying we're not the only one. I give kudos to everyone sitting on this panel, because there's so much trash, it doesn't even matter. We don't even need to compete with each other, because we all need to take action, and we're just part of the solution, not the solution, but we are a big part of that with this application and what we can do. And so that's pretty much the main gist of what I wanted to say today for the starters. I mean, obviously I can get into depth on a lot of things. This QR code is just out of a meeting. My team is right here. I have Todd here, Charles, and Sebastian, one of our engineers that came on in the last year. We're expanding our R&D, and so we're getting some amazing new graduates onto the team. And our VP of engineering also has been, he co-wrote book with the EPA for anaerobic digestion, so we have an amazing team. But come see us. I don't know, what's our booth number? 32. We're way back in the corner over there. And if you scan that, what it's going to do is just give you an opportunity to have a 10-minute conversation. So if you think you have an idea, we are looking for strategic partnerships. If you need help, just book a quick call. We do 10 minutes so that we don't waste each other's time. Just tell us what you need, and then we'll book more time as appropriate. So I really appreciate Dave for putting the panel together here, and thank you for the time, and I hope it was helpful. I'm here for questions, and I'm staying till tomorrow, so if you want to come see me, I think you'll find me, the guy with the big beard, okay? Thank you.
Thank you, Steve. Appreciate that. I'm going to ask Dr. Jordan Klinger to come up here shortly. We should be able to pull up your slides, and if you can, you got the clicker already? All right.
Oh, jumping forward already. All right. Thanks, everybody. Thanks for getting this organized here, Dave. And thanks to Gene for giving me the chance to speak here today. As introduced, my name is Jordan Klinger from the Idaho National Laboratory, as one of the Department of Energy's national laboratories that we're talking about a little bit today. If you look in the booklet, my talk had some self-important, very long title before. I reduced it a little bit here. But basically what I'll be talking about is kind of a case study, if you will, of some of the kind of interesting work that I've been involved in looking at MSW for gasification applications, and particularly how do we make that material flow, or how do we get that garbage or that expletive to flow. Anyone who's worked with MSW, particularly size-reduced MSW or finely shredded MSW, knows that it is not motivated to flow worth a damn. So I get to talk a little bit about that today. But before that, Idaho National Laboratory is located in Idaho Falls, Idaho, the blue star there in the center. But we are a network of national laboratories with a prime sponsor of the Department of Energy. Our goal as national laboratories, in my opinion, not anyone else's necessarily, but is to help bridge the gap between fundamental science and industrial scale research and technology development that cannot be, or perhaps should not be, done at other academic and research institutions, or certainly have industry bear the cost of that. So that is just to say that, in my opinion, why we exist is to help industry folks, such as all of you in the room here today, solve the challenges and problems that you have. Regardless of what that is, we approach them from a scientific standpoint and try to help muscle through that. With respect specifically to Idaho National Laboratory, we are primarily a nuclear laboratory, but within there, I'm a part of a bioenergy technologies group. And this is one partial snapshot of the toys that we get to play with in our large reconfigurable process development unit. This is the Biomass Feedstock National User Facility, one of the designated national user facilities by the Department of Energy, or abbreviated as BUFNUF, which is kind of fun. But it shows kind of a collage of the different capabilities that we have within our group. Effectively, within the Department of Energy network, our bailiwick, or our group's bailiwick, is to serve from understanding feedstock collection, sourcing, understanding how that's done, through processing those raw materials into an appropriate feedstock for a downstream process. Now that process may be direct combustion, it may be pyrolysis as we've heard about, it may be some fermentation that we've heard about, etc. But naturally we all understand that however you're going to use that material requires different attributes of it. Different chemical profiles, different physical profiles, different handling attributes, etc. And all of those will be different based on the starting material. There was a very good question earlier about how do you pair feedstocks with end use cases, and the truth of it is you really have to, it's a local solution, right? You have to use what's available to you, and you have to understand how to transform that into some usable product or usable energy source. Transporting it long distances just is just a no-starter. So with that, I'll talk today more specifically about some work that we've done into gasification of wastes. And with respect to gasification, I'm going to be talking about a few different technologies today, but more specifically focused on entrained flow gasification. But this chart shows a few different simple technologies, from fixed bed to fluid bed to entrained bed technologies. And the main point that I want to get away from, or that I want to take away from this point, is that gasification is not a new technology. Very honestly, none of the conversion technologies that I'm talking about today or any of us are talking about today are especially new. They're adapted from older technologies, but there are technological developments in all of these areas. For entrained flow systems, for gasification, for example, it's a newer technology. It's very highly efficient in converting the material to a synthesis gas or syngas, and it can be economically competitive compared to some of the older technologies, the older Lurgi systems or fixed bed systems that are still in use today overseas to generate petroleum from coal, for example. But these have significantly reduced TARs and significantly improved conversion efficiencies and significantly competitive economies of scale. I'm not going to explain this slide, so don't worry about that. Any material scientists in the room would get excited about seeing this. But this just shows kind of the resultant slag behavior that a gasifier might experience with respect to the types of inorganics that are present inside your feedstock. This is one example to show a phase diagram for different forms of calcium, iron, and aluminum. Each of them respectively change the way that inorganics melt and behave inside of a reducing environment. And this is just to get across that, of course, we all know that feedstock is critically important to how your system performs, but in some cases, or in most cases, especially with MSW, contamination and the chemical profile of that material can prevent the system from working altogether if you don't understand it well. And as a result, if you don't have pre-processing systems that can control either the variability or be able to make it consistent. So to start with, this work is focused on MSW. In this case, when I say MSW, it is the waste from a MRF facility. We've partnered with several of these. This is one particular example where we took the waste after a single stream recycling facility out of Salt Lake City that collects material from about 300,000 homes or so. And this is a state-of-the-art facility, and the material that would have been otherwise bound for the landfill, I was fortunate enough to call them up and have them come dump it off in our backyard instead of at the landfill. Everybody was very happy with me. But we took that material and were able to go through a general characterization of it. You can kind of see that in the bar chart as well in the bottom corner. But the key takeaway there is a lot of material, plastic, paper, and various subcategories therein, but there's a lot of material that's still useful for energy generation that's not currently captured there. So taking that and carrying it through many different types of mechanical pre-processing, in this case no application of heat or no application of chemicals, we're able to generate different sizes of the material, of course, and different quality specs effectively of that MSW with just simple size reduction and screening. There was an interesting talk in the previous session that talked about different technologies for sieving and segregation by particle size, for example. But you can change, there are mechanical technologies that can change the chemical profile and the physical attributes of these materials. Shown here is one of the shredders that we have in our facility. This one in particular is manufactured by Forest Concepts, but following this and an oscillating sieve effectively, we're able to generate different qualities of material that have different inorganics content and inorganics profiles. And this could, for example, represent different grades of feedstock that could be used for different applications. Then, of course, once the material is processed, we want to be able to understand what is this material. Just because we call it MSW doesn't tell us anything about it. That's not a surprise to anyone in this room. There are technologies that exist, and some of the techniques that we're using, developing, applying at INL help us understand this material better between visible sensors, near infrared, mid infrared, XRF, visual sensors, 3D scanners, etc. We're able to combine all these measurements and tools in different AI and machine learning schemes to understand that material and kind of benchmark that with kind of a baseline truth and be able to take that and use these predictively moving forward. So some of that ground truth is collected and shown by some of my happy colleagues here in these photos who are doing some manual separation, segregation of this material. Again, these particular numbers aren't really important because it applies to just this one sample. Any other sample of MSW is going to look entirely different. But after these materials were segregated to various categories, for example, each of these categories, subcategories, and subcategories, and so on that are not necessarily shown here, can be carried through these various sensors and give us a way to predictively detect these materials, quantify these materials in bulk streams, and then be able to act as a result of these materials. So for example, in the case of gasification, there's certainly a prohibitive amount of halogens that can be present depending on the technology, chlorine, fluorine, bromine, et cetera, which are present depending on the types of plastics, the residues from building and construction materials, for example, that have any degree of flame retardant that's been applied to them, et cetera. And these need to be identified and either treated or removed in order to enable them to be either disposed of appropriately or be included in some of these energy generation schemes. So what that looks like, again, there's a whole session previous to this, so I'm not going to spend a lot of time here. But after taking these these positively classified materials and scanning them through with our hyperspectral sensors, combinations of near-infrared, mid-infrared, visual, et cetera, sensors that are on our equipment, we're able to kind of stack all of this data together into a large nth dimensional hypercube and then use that to analyze, quantify, and characterize these materials basically inline. So as material is coming in through a process belt, for example, or being carried off to the next process, we can get real-time chemical signatures of the material. And through development of the AI and ML, for example, this slide shows one confusion matrix, which is appropriate given all the numbers that no one can read, which is confusing. But the important part to look at is the diagonal of that matrix. If it's all in dark blue, that means we have good positive quantification or identification of the material components. And anything that's not positively identified there goes through a second algorithm to more appropriately quantify that, and just generally come to the conclusion that really simple detection schemes can accurately quantify even contaminated or very heterogeneous materials. And what we can do with this information, of course, is take the complex research tools that we kind of looked at before. Don't expect anybody to buy hyperspectral NIR cameras and such like. But there are necessarily very particular wavelengths that give you the critical pieces of information. And what we can do is downsize this from a $500,000 camera, for example, to say if you're interested in looking at black ABS or chlorine detection or whatever it is, look at these particular chemical wavelengths and get a very inexpensive sensor to do that rapidly. So going back to our technology, we say, okay, we have some semblance of understanding of this MSW stream that we're working with now. What do we do with it to try to get it into an entrained flow system? They typically have either a slurry feed or very powder feed if they're dry fed, for example. And anybody who has worked with MSW knows that they doesn't want to go to a powder state for anything, let alone flow. So these next couple slides kind of overview a strategy that we've taken to promote dry solids flow in advanced gasifiers using the application of torrefaction paired with densification and size reduction. So torrefaction is really a mild application of heat to a material. Again, not a new process, but there are new technologies that do this. Analogous to the roasting of coffee, there's a light roast, a medium roast, and a dark roast, and they all give you different flavors of the beans. They all behave differently inside of a coffee grinder, and the characteristics of the coffee are all dependent upon that. Similarly, torrefaction could be applied to biomass materials, whether it's tree trimmings, grass clippings, biosolids, digester solids, whatever have you, and it gives you different properties of the material. The carbon the carbon content changes, the amount of volatiles relative to the fixed carbon changes, or just the ability of that material to act as a fuel changes as a result of that. And you could take advantage of these types of technologies in order to, number one, embrittle the material so its size reduces much easier and much more uniformly, as well as give it better properties to act as a solid fuel. Like I was just saying, this slide shows kind of a visual representation of this material as it's torrefied to different degrees. All these particles show stages of drying at the top to processing around 300 degrees C. But as a result of this, we actually also see improvements in throughput as well as size reduction performance within mills. So much so that if only by doing this and removing a portion of the volatiles, you effectively gain more energy in return on top of what you would spend to size reduce the raw material. So just energetically, if you need to go to a fine grind size, it doesn't make sense not to do this type of a process. Combining that with densification, we arrived to a few different conclusions. One is that the powdered biomass or powdered MSW in general takes a light, fluffy material and makes it more light and more fluffy if we just size reduce it. Again, that doesn't surprise anybody. And when we have a pelletized version of that material, of course, it's more dense. But if we have a pelletized material and then we micronize it, we end up with a very dense aggregate. Combined with torrefaction, we can achieve the right conditions that enable a micronized feedstock to act as a micronized granular feedstock, even though it wasn't necessarily exhibiting that behavior before. So on the right-hand side, we see a plot of the specific flow energy with respect to effectively the applied shear rate. And this shows basically a relationship to how much, if you're pressing on a bulk material, what's that material's resistance to flow or the energy that's dissipated in that bulk material as it begins to flow. And on the top two, the green and the blue show just pathways for raw micronized feedstock and torrefied micronized feedstock, but the bottom two are torrefied and pelletized feedstock compared to just play sand. So the most ideal feedstock probably that we can imagine with respect to mechanical flow performance is sand. You almost can't stop it from flowing or from getting in your sandals. But in this case, we developed a process to make biomass resemble granular material in one of the most extreme cases. So this chart compares, again, some more of these flow characterization results. I'm not going to spend a lot of time here, but in comparison to steam explosion, in this case for a corn stover, which was an agricultural residue, comparing the densities and internal frictions and details that I'm happy to talk about, but I'll save those details for an offline discussion. So taking this outside of the laboratory environment a little bit, we also pride ourselves, and my colleagues here, Lynn Kolevitt, Neil Yancey, Vicki Thompson, we're in booth 29, come talk to us. But a lot of our research, we pride ourselves in partnership with industry and trying to take things at least to a reasonable pilot scale if we can. So this slide shows some pictures from a pilot scale campaign where we generated north of 200 tons of this material process, as I just talked about, going through densification and torrefaction of this process to produce a torrefied powder in partnership with one of our industry partners, GTI Energy. And they took this material and they were able to flow it in their Entrained flow gasification system. This has been done perhaps only a few times, but the leaders are primarily over in Europe. And in the US, Entrained flow gasification of biomass and biomaterials is almost non-existent. So this was a good step forward for us to be able to take this and apply this to these advanced technologies. That being said, of course, these materials also lend themselves to any other type of technology. This slide shows another example of when we partnered with a more simple fluidized bed technology, which is more accommodating to different physical formats and physical attributes about the material. It was co-densified, in this case, with a sawmill residue, and they were injected into their fluid bed system, and we had a successful number of tests there. And of course, all of our reconfigurable processing equipment that's heavily instrumented, as you might expect from a laboratory, gives us the ability to very quickly and very accurately quantify mass and energy balances that you may need to use for TEA, reduction of risk for investment, et cetera. With that, I did want to give a quick plug also to the National Laboratory Gasification Consortium. This is a kind of a conglomerate of 4 of the national laboratories led by the National Energy Technology Laboratory. INL is a part of it, as well as Oak Ridge and the National Laboratory of the Rockies. And we are collectively trying to move the scientific field of gasification forward in order to help enable the industry of gasification. So whether it's a feedstock supplier or a gasifier operator, if somebody is interested in this type of a pathway, please come talk to me. Please email the folks on this slide. We are always interested in having industry feedback and industry guidance on relative challenges. With that, thank you.
Next up is Varsha Walsh. Thank you.
Are you ready for me? Oh, thank you. All right, everyone, I know we are very close to our reception, so I'm going to keep this fun and short and sweet, but hopefully give you a little teaser, and if you're interested, we can definitely chat more. So I'm Varsha. I am the CEO and co-founder of Offstream, and we work with largely organic biomass owners, people who are sawmills, lumber mills, pulp and paper, have excess waste product and are looking to stand up a new revenue stream by converting it to something valuable and ideally also generating environmental attribute credits. So before I jump into my presentation, I know we've talked a lot about MSW. Just want to get a sense for the room. How many of y'all have access to organic biomass? Okay, so not too many. You, yes. Okay, thank you. And then, so what I will talk about today is mostly relevant to organic biomass. And the reason is that for carbon credits, they're generated basically based on taking biogenic carbon and putting it into a permanent storage location. So inorganic carbons don't qualify today for carbon credits that exist in the market. There are other types of environmental credits. I won't be talking about them, but if you want to chat about them, let's definitely do so after. So in the next 10 minutes or so, I will cover mostly just 101 for folks who are interested in carbon credits, but maybe have been skeptical, want to know what they even are, how to get them. And if you think you can qualify, definitely come find me after. Our customers are typically operators who want to get carbon credits without having to build a whole team to figure this thing out. They have compliance teams that help them with EPA regulations. They don't really want to have to disrupt their day-to-day operations to figure out if they can actually make money from biomass carbon removal. Super basic, a carbon credit is basically a quantified, you could think of it as an asset, so to speak, that is representative of 1 ton of carbon that is permanently removed from the atmosphere. So folks like Dave probably generate different types of carbon credits, emissions reduction, emissions avoidance. There's a large movement recently towards carbon removal, and these credits can often actually be sold for $150 to $250 per metric ton of carbon. So the reason we're talking about this today is that the old world of credits were sold for $10 or $20 a ton. This being a huge step change makes it more appealing for a lot of folks who are trying to basically unlock new revenue. So I got into this space because I was actually working at an agriculture company, and we were trying to generate carbon credits to help growers transition from traditional to regenerative agriculture. And at the time, this was in 2019, I just really wanted someone to tell me what to do. And I was like, is this real? I don't understand. When you Google it, there's not really a great source of information out there. And so I can definitely talk a little bit about the market right now, but what I've seen over the last 7 years now is that there is definitely a steady, not meteoric rise in funding towards carbon removal. And ultimately, as we approach 2030, the same tailwinds that are affecting Dr. Wong and BayArea Compliance's businesses are affecting companies who basically know they can't reduce their emissions to zero, know they need to at some point at least show that they're trying, and carbon removal credits give them an opportunity to basically fill that gap or plug the hole of what they're not actually able to decarbonize in-house. I will spend a little bit of time talking about biochar today. Biochar hasn't been mentioned, but is often has lots of connotations, but is basically a product that is a co-product of pyrolysis or gasification of organic biomass, and is a very common and kind of like quick path for a lot of folks interested in carbon credits today. The capex involved can be 5 million, not 50, and so it's a lot easier entry point. And a lot of folks that we work with are basically dealing with the waste product, can purchase the unit, get it up and running in 6 to 9 months, and be generating hundreds of thousands in carbon credit revenue and then potentially also biochar revenue after. What I see today in the carbon markets, really in my day-to-day job, is that there are lots of project owners that have a waste biomass. Maybe it's being piled up and landfilled, so rice husks is a common one we work with a lot, biosolids, manure, and there's a lot of friction, there's a lot of questions on what's actually possible to be done, but a lot of operators are closer to getting a project off the ground in the next year that could generate credits. And for the most part, we see a lot of brand new entrants to this market. So people who've never operated any sort of processing facility in their life, producing biochar, and that's where things kind of fail, is that they're not able to execute, but the folks in this room are very well positioned to do so. So I'm excited to be here. The number one thing that makes or breaks whether a project can generate carbon credits today is the feedstock. And this is largely because purchasers of carbon credits are really concerned about deforestation. So they want to know that if they're buying a credit, that the feedstock that fed into that credit wasn't grown for the purpose of being cut down and then made into biochar or into bio-oil and then generating a credit. So this is the area that we spend 50% of our time when folks come to us and they say, hey, I have this project, I think I could get carbon credits. It's actually, in this case, rice husks that used to be landfilled. Can I use them? And the answer is it always depends, unfortunately, but there are definitely some down the fairway feedstocks, and then there's some edge cases. And so in general, what we see is really compelling today for credits are ag residues. So specifically, if your residue was getting burned, you're totally in the clear. But even otherwise, if it was kind of laying and releasing methane or carbon into the atmosphere just in its steady state, pretty positive. Forestry and sawmill residues. Here in the US, it's a little trickier because some of the standards really want to see FSC or PEFC certification. That's really hard on privately owned land, but there are some ways around it. Clean wood waste, yard and tree trimmings. So all of these produce typically easier projects. Obviously, we've talked a lot about the challenges of MSW and the volume of that feedstock, but also are considered kind of strong candidates for credits. So I'm going to go through just a high level, sort of the 3 most common pathways we're seeing with respect to carbon removal credits, and recognize that our job is less as a technology consultant. We're not doing any of the design work. We're typically a layer to help with all things data collection and reporting. So pathway number 1, bioenergy with carbon capture and storage. So this would be any sort of bioenergy, so ethanol, any of the work National Energy does. Lots of projects exist already today, and new ones are being stood up where basically CCS is implemented on top of an existing bioenergy facility this removes carbon because it's capturing biogenic carbon and storing it permanently. There are very few operating BECCS assets in the world right now and only 3 in the US, but it is seeing the largest amount of funding in the carbon removal landscape because of the scale it can present to folks, and also because it's considered kind of a nice mix of durable but also secure. Pathway 2 is biochar, so I mentioned this a few times. This is just one example, but most of the folks that we're seeing in biochar are using pyrolysis, specifically rotary kiln pyrolysis technology that can process 10 to 30 tons per day of feedstock, and are often producing a physical biochar product, syngas, and a bio-oil, and sometimes also a fourth co-product, which is like a wood vinegar. Some folks do add an ORC onto the syngas output to produce energy, and so this is, it's not mega scale, so to speak, but it is kind of a nice circular economy solution, allows them to claim carbon credits and typically ITCs from energy production. So this is like 95% of what we see in the market today, because easier to stand up, easier to get off the ground, and the carbon credit market is very interested in biochar because they can, you know, like a buyer can fund a project and then see it come alive in 1 year and have less concern about whether it'll actually exist. It's also probably like the highest technology readiness level of all the work we see. And then the last pathway, which is a little bit more niche, is basically biomass waste slurry injection. So this would be often taking biosolids, or really often just biosolids, and slurrying them, injecting them into a class 1 or a class 3 well. This is very compelling for the carbon credit market, because often like this waste product is a real one. Customers that we work with are getting tipping fees for receiving it and then also generating carbon credit revenue. So they're getting at least 2, if not 3 revenue streams. Okay, super quickly, how a pile of biomass becomes a carbon credit. This is very generic, but essentially what we're seeing today in the market is a lot of folks kind of piece together a project based on some biomass that they have access to, and then some end use that they have for it. So based on the quantity of biomass you have, your appetite, you might choose a biochar option, or you might choose bioenergy. And essentially what we see is really effective is, before moving forward, doing a quick eligibility check. Like, is this project going to generate carbon credits the way that I hope to? And then secondly, like, how long is that going to take? Once a project is kind of designed, like there's a straw man more or less, there are pre-eligibility checks that you can, like, that we see our customers formally do. So there are standards organizations called voluntary carbon market registries. These folks basically know that a lot of people need a little bit more substance before they're going to green light $10 million, $20 million project on this, and will basically review just at the idea stage what your project looks like, and then allow you to list that project as a like forward-looking one. And so that's basically the next step that has to happen. And between steps 3 and 4, a lot more happens, right? Like the whole project gets built, but once it's live, it's a production-based standard. So every year you need to monitor the activity, track and record basically a life cycle assessment. So how much energy went in, how much energy came out, what was your net carbon removal impact, submit that data, and then get credits and sell them. So between stages 1 and 3 are a lot more planning, and then 4, 5, and 6 are really all about executing. Just 2 seconds on some things that we hear, and if this resonates with you, definitely let's chat. But for a lot of folks we meet, they want carbon credits, but they really need a little bit more proof in the pudding before they'll take a step forward. Simplicity is super valuable, and ultimately there's just a lot of I don't know where to start, essentially. So if you think about what I just outlined, there are sort of 3 phases of carbon credit certification: figuring out if you're eligible, then doing a one-time certification that's like a per site basis, and then every year doing live ongoing data collection. Our platform essentially streamlines this from end to end. So at Offstream, we work with project developers at the feasibility stage and help them answer how much money am I going to make from my credits, and can you definitely confirm I'm eligible? And then once that's greenlit and a project is a go, we typically advance and kind of hold their hand through getting their site certified and then doing that ongoing certification. I'll leave you with a couple of case studies in case this is inspiration for you. So one of our customers, Earth Care, actually is a technology developer, but also a project operator. So their technology converts poultry litter and swine waste into physical biochar. They also have a like the gasification from their unit dries the feedstock. So some folks just use it just as a dryer. We worked with Earth Care, who actually did all this carbon credit work on their own manually, to then translate them into our platform, and they saw a pretty big increase in credit revenue just because their books were clean. So that was one. Another one of our customers is Sutton Lumber, family-owned lumber mill in Arkansas, and they basically saw their revenue stream from delivering their wood chips to a paper mill kind of dry up. And so they had leftover wood chips every single month and purchased a BET, a Biomass Energy Techniques rotary kiln, and are basically funding that with carbon credits. And so their payback period on that kiln is 2 years. It's not huge dollars, but it's all about small steps towards these new revenue streams. So just another case study to consider. I will leave you with my information. So for anyone who is interested and curious about this, we do feasibility studies one-off. We're really passionate about bringing this revenue stream into the hands of more people and not having there be an ivory tower around carbon credits. It's not really effective for the market. And so if you're interested, please reach out. This email is our team, or my email is just varsha@useoffstream.com. Thank you.
Okay, fantastic stuff. Don't get too excited. The bar doesn't open until 5:30, so we got a few more minutes together, so calm down. Gene, are you going to help me with Q&A?
Absolutely. I'll walk around with the mic.
Fantastic. So we have a few minutes, and we already have a question up here. Did you want a part two to your first question?
No, hang on, John, because I've got people online. Grab the mic.
No, I won't part two my first question because I know that could get really, really deep, and that could end up an entire session of its own. My question is for Ms. Walsh. Very good presentation. I appreciate that. I think this is something that a lot of people really fall short on, that there is a lot of potential for, these carbon credits are very beneficial for other larger industries that are big generators that, can purchase these, and it can have the potential to offset a lot of cost for other processes. So my question would be, who's to say that in that scenario that if you're doing a landfill diversion, methane gas is 80 times more potent than CO2?
20.
So by
like 27, 23,
okay.
27.
Right? There is a divisible scenario
more
there.
Than 8, that's fine.
Yeah. So who's to say that if there was a scenario where someone was going to build a MRF, a municipality, we're going to build a MRF, but we do kind of struggle on finding the return in that. But we're going to divert 200 tons per day from the landfill. How can someone like that kind of go down that path of, we are legitimately reducing our landfill footprint, which reduces CO2. There is some tonnage there to be gained for carbon credits. So have you seen that, and is that a viable scenario for some of these folks that are in here in the room that may be part of a municipality that has looked into this, but they fail to see where some of the monetary benefits can be, that they can team up with larger industries, maybe even in their own communities?
Yes. The question was, have I seen carbon credits for basically the emissions avoidance of landfill diversion, right? So the short answer is yes. There are lots of different types of carbon credits. They're defined by methodologies. You can kind of think of them as recipes. So you follow the recipe and then you generate a credit. And there's different types of credits. There's emissions avoidance, and then there's carbon removal, and they get priced differently. So I'm not an expert. Is anyone else on the panel an expert in landfill diversion credits? There are methodologies for landfill diversion. When credits are getting generated to avoid an activity, there's this tricky nuance that I won't go into too much around, like the financials of it. So if the project would have happened without the credit, it's really hard to get a credit because you're basically getting paid to not do something. So that's where, in the voluntary market, this carbon avoidance landfill diversion credit has not really taken off because it's been hard to prove that the carbon credit was mission critical to that project happening. But one way we've seen this play out is by just quantifying that impact and reporting it into a downstream partner's greenhouse gas reporting. So that's probably some of the work BayArea Compliance does. And the way that would be done is through basically a life cycle assessment that tracks what is the baseline of methane or carbon emitted from that landfill, and then what is, what basically claiming that reduction. One ask I actually have for national labs, I don't know if it's INL, but maybe NREL, is actually better quantifying methane emitted from landfills, because one problem we run into is that our customers don't get credit for that emissions avoidance when they use, let's say, when they divert from the landfill and they do carbon removal. So if anyone is working on that, I really would love to speak to you. Thank you.
Cool, excellent, thank you. Any other questions? Did we have one over here? No? Yeah, we have one over here, Gene.
Yes, I have a sawmill, and I create a lot of sawdust. Now, I don't operate it. I have somebody who likes to do that stuff. But he just puts it in a big pile and lights it on fire. So my question is, for a mom and pop who has a wood miser LT35 and he's cutting 4 to 5 pines a day, can he go to someone and say, here, I've got all this stuff. What can I do with it? So that would be somebody to come to you.
Yeah, yes, and we can definitely talk after this. Either they could purchase something themselves or they could give that biomass to someone.
Cool, okay, thank you. Anybody else? I had one for INL while you're making your way that way, Gene. We got a question over here. Does INL have a program for work for others, for instance? Does your lab do that?
Yes.
Oh, okay, good question.
Longer answer. Booth 29. They're very, very happy to talk about it in grave detail.
So if you needed a specific specialty or functionality that the lab does, you can actually hire the lab to do that work. So just wanted to put that out there.
Several different ways to engage the lab, from taking advantage of government grants to direct partnership, like a work for others. So yeah. Lots of different ways.
Very useful. So make sure you visit booth 29. Yes, sir.
My question's pretty, I guess, general to the full panel here. Waste to energy seems to get a visceral reaction from the environmental community. I mean, almost 100% opposed. I know California has not yet come down on chemical recycling and whether or not it's going to support chemical recycling as a, quote, responsible end market. Can you comment on both of these issues, since we have some panelists here from the West Coast, as well as, the whole waste to energy discussion? Because it seems to be, we all want this issue of recycling to work at the 8 and 7% level. We're not going to get anywhere if we can't agree on at least how we're going to process this stuff. And it seems like every time we make progress, the environmental community can seem to come together and say, this is something we need to do. And I know even from the zero waste standpoint, whether it's U.S. Green Building Council, which is true, or U.S. Zero Waste USA, they're just 100%. You mentioned waste to energy, that doesn't qualify. It's just bad. And so I'm hearing a lot of really positive discussions around progress, but we really didn't talk about the fact that there's a huge opposition wall here that we need to overcome if we're going to make this a reality.
Yeah, that's a great question. I don't know if anybody wants to take it. I was introduced to a new term in my vernacular. You've all probably heard of NIMBY, right? Not in my backyard. So then now the new one is cave people. Have you heard of cave people? cave people are citizens against virtually everything, which that was a new one for me. But you're right. I think we should really center around the issue, which is landfill diversion, right? I think everybody can kind of coalesce around that. In my opinion, I think waste to energy just covers so many different types of technologies, and everybody kind of just assumes it's, you know, the old stinky waste to energy plant that was built in the 80s that they're petitioning to get rid of. So I think there's definitely some education that needs to happen. But
I just wanted to echo that. It is like a branding issue in that way, because you're, from one perspective, the waste to energy was known for mass burn. And that is still happening, right? It's just that long tail off of that. And we have to say that there's other ways to convert that energy. So that's why even with my team, we always say, you know, trash to fuel. Just even that word makes a difference. And I do go into California, and then when we start saying energy, then, you know, they want to stop talking to you. So we can't even use that word. But then when they see the application, they're willing to talk to us. So it is very much for me in the marketplace, it's vocabulary. Vocabulary makes the difference.
Yeah, I also want to have my comment about waste to energy, but I put this in plastic waste perspective. For example, we have a lot of agricultural plastic waste. And then when we talk about plastic waste, right, it's sometimes it's just a matter of like economics. We can recycle all the plastic waste just because of what I just mentioned, prime price so cheap, overcapacity, blah, blah, blah. So California do not really support, for example, if you want to do pyrolysis, they actually treat pyrolysis as like incineration. So there will be different set of regulation and rule and laws. So there's a solution, you know, in my way of thinking. One is, okay, we might have to ship something or the waste or plastic waste to other states like Nevada or maybe Nevada is the most nearest state that we can do. And secondly, as also I mentioned, and yesterday there were panelists talk about EPR. So we hope that there's an EPR system over there to enable the financially recycler to recycle plastic waste. And I think we probably have to wait until the EPR system over there and also to be enforced with the support of brand owner and also the manufacturer of like chip tape or film to support financially the industry. And at this moment, I don't really see or haven't seen any of the plastic recycler for agricultural plastic waste successfully run their operation. In actual fact, you know, not only like plastic waste from agricultural industry, we never really seen any of the factory, or there are more and more people in recycling of plastic got out of business. And most of the people always think that this is really a sustainable business. Actually, it's not. Yeah. Yeah, I don't know where you want to comment.
I guess I don't have one.
I think we're sharing. Yeah.
I have all kinds.
Number 2, I think. Or maybe you turn it on. Use that one. This one.
Okay, so all kinds of technical difficulties. I just wanted to also expand on that. I agree that it is quite confusing, the responses that we receive from different industries. You have people who only want recycling, only want it within 50 miles, right? They don't want it in single loop, they want it in circular economy. They don't want it to go waste to energy, they don't want gasification, you know, they don't want mechanical recycling. So everybody certainly has an opinion on this, but I think what we really need to do is educate people on the right way and the best path for each material. And that's really done by identifying what the source is with the generator. I mentioned earlier that we start at procurement, and we do that so that we have a solid path and we can be all on the same page. ultimately, it's really also important to understand what the goals are of the company. We have companies who, their ESG metrics are really what they're going for. Others are going for carbon credits. Others are, looking at sustainability. And some are just, they have a big waste problem and they need to solve it. So it might go to the landfill or waste to energy. So we just really have to understand the environment, the areas that we're working in, and the logistical complexities as well.
Cool. Yes, good thoughts. Anybody else have a comment? No? I think we have time for maybe one more question. But your comment is not lost on me, because I have heard that from time to time. And then your point is people are like, well, unless you're recycling it indefinitely, it's not really recycling. And I'm like, really? Come on, man. So you do run into that. It is part of it, but I think there is an educational process.
And fortunately, here in Florida, we do recognize waste to energy as well as pyrolysis as recycling in the state.
Cool. All right. I don't know that we have any questions left, so maybe we'll adjourn early. I'm going to grab my panel for one quick picture, and then I'm going to release you to your cocktail. So, Gene, I'm going to turn it over to you if you want to take us to break.
All right. Thank you, everybody. Thank our panel. Appreciate it. And we are at break we're at reception.